this was in what I told you. There are two cases, right? In what case have we used? What say? Is the thermal boundary layer is much thicker than the viscous boundary layer. All right. Sometimes it's the opposite, and let me tell you. You know when this is true? For molten metals and plasmas. 95% of you chemists, you don't care about that. You care about the other one. Let's do it. Let's do it together, okay? So this would be case 2. Now we have YCV is much bigger, is bigger than than the thermal, even if they are more or less the same. Now the story changes. And why does the story change? Because, and I'm starting to draw faster and faster. So now we have, let's say this is our viscous boundary layer. And does everybody agree with my drawing of the viscous boundary layer? Zero on the surface, U infinity out there. It bends right at the value of the viscous boundary layer. And let's say now we have a thermal boundary layer, which is smaller. This is the opposite of the other case, right? And I'm going to make it a little bit shifted, but if I make a thermal boundary layer, now it starts at Ts, here this is Ts, and goes to T infinity. How do I go from here to there? Where do I bend? This one, right? Thank you. Now the story got interesting. The story got interesting because the velocity inside the thermal boundary layer is not anymore U infinity. Right? The velocity in the boundary layer is something else that is less than that. You see that? It got interesting, of course. So let me tell you some more about the viscous boundary layer, right? And so here's something important. Remember I mentioned to you a few classes ago that conduction heat transfer, right, is very similar to mass heat transfer and very similar to fluid mechanics and even in some cases of electromagnetics. They are all part of a family of equations called parabolic equations. You don't need to, that's not in the exam. But the funny thing is that you have some fluid mechanics and heat transfer are problems involving diffusion, right? So for heat, we have alpha equals K over rho Cp, rho C, right? And this is thermal diffusivity. For fluid mechanics, we have nu equals mu over rho. And this is called the kinematic viscosity. And both have units of, both are meters squared per second. So this number Prandtl is the ratio of nu over alpha. So what this Prandtl number you're going to see coming so often is the relationship between how fast we transmit viscosity, velocities, right, versus how fast we transmit heat. What do you think a metal is? We already discussed this, but what do you think a metal? Who do you think has higher Prandtl number? Oil or molten or mercury? Right. Oil is very viscous, and mercury is very thermally conductive. It's a molten metal. Mercury is very small. Oil is very big. Right? So this is a dimensionless number that is intrinsic to the fluid. So here is something super interesting, because if you remember, we said we said for the case of penetration of heat, when it's a semi-infinite solid, was square root of alpha t times, I don't know, it could be square root of pi or similar things. But for velocities, we have, this is the penetration of the velocity, right? This is the viscous boundary layer, right? Equals something that is squared of, instead of alpha t, the time we said was x over u infinity. Right? That's what we said time. And now instead of being alpha, it's going to be nu. You follow this? This is a diffusivity. And this is time. This is the same as alpha t, but it's nu x over. And now we used to have, for a semi-infinite solid, was square root of pi. Do you remember? Square root of pi is more or less 1.77. But in this case, is 3. This value of 3 is not trivial at all. This comes from solving very difficult equations that don't give you an error function now, give you something else. So compare with you see that these two equations are very similar. In one we have nu, and the other we have alpha. But nu and alpha are the same idea. One is diffusivity of heat, the other is diffusivity of momentum, of velocities. The x over u infinity is the t. It's the same. We go from the semi-infinite solid to the thermal boundary layer to the viscous boundary layer. And then I made the note. This is true, but for the case 1, right? The one that has much bigger thermal boundary layer. The fact that it's a 3 is because the velocities here are not constant. Yes?
YCV, is that YC of diffusivity, or is that two?
This YCV is this one here. This is YCV. Thickness of the viscous boundary layer. Good? Let's stop here. I'll see you on Monday to wrap this up. And that's the last that goes for the exam.